For today's lesson, we are going to talk about complex numbers. This is something that you've been exposed to over the years in different ways. We may introduce even yet another way. Complex numbers are essentially every combination number that you can possibly think of. We're going to focus on just one particular variety, and the ones that are going to be taking the form of a plus bi. With that kind of form, you've got a couple things. Number one, you have the a part, which is considered the real part, and then you have the bi part, which is considered imaginary. When you have these kinds of numbers, you can have simple, just real numbers like 5 and 10 and negative 2, or you can have purely imaginary numbers like negative 3i or 2i or just I by itself. Sign, positive, negatives, all those still play a part. Just to kind of remind you, that I is equal to the square root of negative 1, or I squared is negative 1. This one is probably going to be the one we're going to be kind of exposed to more often in this example. Just to kind of, a lot of this is going to be review, and a lot of this may be just kind of you getting used to seeing it this way, but it's not complicated at all. This is actually a relatively easy lesson. When you look at complex numbers, they all have complex conjugates, some that matter and some that don't. For example, 3 minus 5i, the complex conjugate is 3 plus 5i. For the second one, you have negative 8 minus 1/3 I, or you could have negative 17i, or 37 is just 37. 37 doesn't have an imaginary part, so you can't change its sign. So really that's 37 plus 0i. So 37 minus 0i doesn't really change anything. So whole number real values, or actually just real values where they don't have an imaginary part, when you find the conjugate, it won't matter because it doesn't have an I piece to it. Okay, what do we do with conjugates? Well, we use them for division. And I want to kind of walk back for a minute and talk about how you can multiply complex numbers together. Okay, this is what you've always done for, actually, let me back it up. We're just going to FOIL this all together, right? So 4 times 4 is 16. Then 4 times 7i is going to be plus 28i. Then you're going to have here negative 7i times 4. That's going to be negative 28i. And then you're going to have minus 49i squared. I want to call your attention to this part. The rest of that seems pretty self-explanatory. Remember that I squared is equal to negative 1. So what really happens here is this becomes plus 49. And that's a pattern you can kind of rely on. It's going to always do that when you see I squared. It's just going to change the sign of the object. When you're combining complex numbers, you always want to combine all like terms before you finish it out. Right? So 16 plus 49 is going to give you 65, plus 28i minus 28i is 0i. So really we're just going to have 65 as the result of that product. It's really 65 plus 0i, but I don't need to write the 0 piece of that. Hold that thought because we're going to use this kind of process to do division with complex numbers. When we have division or a quotient in a complex number, you're going to do it this way. It's going to be 3 plus 5i over 4 minus 7i. I want the complex conjugate on the bottom. So we're going to say 4 plus 7i, and we'll do the same thing on the top. We've done this before, but not in this context. Now we just did that bottom part in the previous page, so this is 65. I'm going to go ahead and FOIL the top part together. Now this one will not, well, I won't have anything to cancel out because this is, the bottom part here is the difference of squares and the top part is not. So it will simply multiply and you combine like terms. In this case, 3 times 4 is 12. 3 times 7i is plus 21i. And then 5 times 4 is plus 20i. Negative 5i times 7i is going to be plus 35i squared. And remember what we said, that really becomes minus 35. Let's collect all our like terms. 12 minus 35 is 23. Actually, negative 23. Then it's going to be plus 40, actually 21 plus 20 is 41i over 65. So here we're going to, I could leave the answer like this. I could also simplify if possible. Most of the time, we really want our answers in the form of a plus bi. So I'm going to separate the fraction like this. 23 over 65 plus 41 over 65i. I would accept either one of these two, but I think more often you're going to see that second answer show up more than most. Okay? If you can simplify, if these are prime numbers, 23, 41 are prime, so you clearly don't have any common factors. But if I could simplify, I should definitely simplify this. Okay, just to do real quick, pause the video, try this on your own, and then when you get ready, click play and see if you get it right. No, seriously, pause it. Okay, 7 plus 3i over 9 minus 5i. 9 minus plus 5i. The bottom part, if you noticed the pattern earlier, it really was a squared plus b squared turned out to be what it was, right? So we ended up getting 981 plus 25. That gives us 106 on the bottom. If we FOIL the top part together, we're going to get 27 plus 35i plus 27i, then plus 15i squared, which is really going to be just minus 15. So we combine all these values together, double check my numbers. Yep, I messed up. Y'all caught that, I hope. That is 63. That makes a lot more sense. So 9 times 7 is 63, and 3 times 5 is 15. So 63 minus 15 is 48 plus, that's going to be 62i, all over 106. We can separate that. We also notice that these are all positive, even values. So I can go ahead and at least divide by 2. Maybe we can do a little bit more. 24 over 53 plus 31 over 53i. If for a reason you don't have the same denominator once you simplify, there is absolutely no problem with that. Those are totally fine to get that way. Not a problem at all. If we keep going, how do you graph with complex numbers? It's actually quite simple. If you will pay attention to the a and the b in that complex value, you're going to get that to be exactly the same way as you would graph any other number. Okay? So for example, if we graph, let's say, point A, 5 plus 9i. If you notice the axis, the real axis is the positive x-axis, or the x-axis in general. The imaginary is going to be your y-axis. So this part is the real part, and this part is your imaginary. So if you can think about it in terms of like x and y, it's exactly the same, right? So if we go over 5, so 1, 2, 3, 4, 5, and up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Point A turns out to be right here. Point B, on the other hand, would be -3, -7. So 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7. This would be point B. All right. A few other things about this, which we'll get to in just a minute. You see this word modulus. Modulus is essentially the distance formula. It's just like what we had before as the magnitude of the vector, which the distance looks like this. It's a lot like absolute value. How far is my point away from the origin? It's the same thing. This is A and this is B. I'm going to use the Pythagorean theorem and I'm going to find it that way. So anytime you see the word modulus or absolute value, or you see the symbol here, absolute value of z, they just want you to find the Pythagorean theorem. How long is that, or how far away is that from the origin? The other side of that isn't just the distance or the modulus, it is the angle, or something they call the argument. Remember that if we wanted to find the angle, it's just tangent inverse of the, in this case, it's going to be b over a. And the same rule will apply. If a is negative, add 180. In this example, or in all of this really, A really is the x-coordinate, and B is equivalent to the y-coordinate. So all of the formulas that we worked with vectors and things like that, if you kind of just substitute A and B in instead of x and y, you're going to get the same exact formulas. Okay, just for example, in vectors we had x equaled r cosine theta. Here we have A equals r cosine theta. B would be equal to r sine theta. So if I wanted the x and y coordinates, or the A and the B pieces of this, the sides of my triangle, the actual real and imaginary components of this thing here, I'm just going to do it like before. Okay. In terms of writing a complex number in what we call polar or rectangular form, we have to think about it. I've already given it to you in rectangular form. This is rectangular, A plus BI. You go left and right, or you go up and down to find your position as a rectangle, like left, right, up, and down. Okay, that's super easy. You already know what that is. The polar form is something new, right? The polar form looks like this. We say z equals r times the cosine of theta plus I sine of theta. What I really want you to kind of realize is that this format is kind of like a fill-in-the-blank thing. It's not something you have to calculate or work with. I'm going to create this kind of template here, and this is when I ask you, for the polar form of a complex number, you're really going to just fill in these little blanks. And this blank is r, and this blank is theta. It's the same thing for both. That's really bottom line. If I'm really trying to boil that down to the bottom, this is all we're doing. For example, let's look at example 1. We want to find, if I want to write this in polar form, that means I want to write it in the form that you see up top, this form right here. By the way, that's really long, and there's a shorter way to do this. We call this shorthand, or I guess it's a shortened version. It's RCIS theta. The C, actually, let me change the color of that. The CIS comes from there. And it's understood that if I just used R theta in that, you're good to go. And I typically write my solutions in the shorthand way, not the longer one. So I want to find R. It's going to be the square root of 3 square roots of 3 all squared plus 3 squared, right? Pythagorean theorem with the A and the B pieces. Well, this is going to be, it's going to be 9 times 3 plus 9. That's 36. So the square root of 36 is just 6, okay? Theta is going to be the tangent inverse. Now I've got positive values, so I don't really worry about adding or subtracting the negative values, right? It's going to be 3 over 3 square roots of 3. That's really 1 over the square root of 3, not equal to. Right, this fraction reduces to 1 over root 3. That's really familiar. If you look at your unit circle, you're going to find this. Now, I can still use my calculator. That's going to be quite simple for me to do. If I wanted to find that out, it would be tangent inverse of 1 over root 3, or you could type in that entire fraction. This gives us 30 degrees. Now, whether you go back to the unit circle or you draw your triangle in the first quadrant, right, this would be where the y part is 1 and the x part is root 3. This would be 2. Of course, this is your 30, 60, 90. I don't care how you want to remember that, or you can trust your calculator for most of these things. So I ended up getting this way. My solution here would be 6 CIS 30. And that's really all I would have to do for this problem. Okay, let's skip over to the other example. Here at the end, it's asking me to go backwards. If I have polar form and I want rectangular form, it's really, I just want to work it out. I'm going to take this 2 and I'm going to distribute that into these two parts and just simplify this piece and this piece. And I really want to end up with A plus BI, and that's it, right? So we're going to have 2 cosine 150 plus I times the sine, 2 times the sine of 150. If you think about the 150 degrees, that's going to be 2 times the square root of 3 over 2, actually it's negative, plus I times 2 times 1/2. Now I'm using exact values, I would essentially use my unit circle if I were you, or my left-hand rule, or I can do it like this. This is 150. That means that's 30. That means there's a 1, there's a square root of 3, and a 2, and this is negative. That allows me to get the cosine and the sine exactly without having to do a whole lot of extra work for it. This becomes negative root 3, because the 2's just cancel, plus the 2 times 1/2 is just 1, so it's just the negative root 3 plus I is how we would end up. The very last part of this is quite simple. If I look at the question, if I look at the point A, it says 2 cos 60 plus I sine 60. If I want to graph polar coordinates, then I really look for R and theta. The extra bits about sine and cosine don't matter. So I'm going to do this first. It's just like how you graph rectangular coordinates. You have left, right, up, and down. Okay. If I go to the angle measure, and then I'm going to go use the radius, right? Here we turn in circles to a right angle, and then I walk forwards or backwards based on what my radius is. So for point A, I'm going to go to 60 degrees first, and then I'm going to go out 2 steps to the second circle. That's point A. Point B, not this part, but the part that's written or typed, is 4 cosine 240. So I'm going to go to 240 here, and then I'm going to come out 1, 2, 3, 4 circles out from the center. Okay, and that allows me to find that coordinate point B. Now let's suppose that you had a negative 2, 150 as a polar coordinate, not in trig form, but just in its polar form, not trigonometric form. I want to know, how can I get to this one? Well, I'm going to go to the angle first. And then instead of walking forwards 2 radii, we walk backwards 1, 2. So this one becomes all the way back here, right? And so this opens the door that there's usually about 4 different ways that I could tell you to get to point A. I could tell you the direct way, like they told you here, go up to 60 and go out 2. I could also tell you to go backwards the angle, go negative 300 degrees and go out 2. I could also go back all the way over here. If I follow this backwards all the way here, right? That's 240. I could go to 240 and then back up 1, 2. So you have a negative 2 radius. Or I could go back down this way. So this is negative 120. And then I could say negative 120, negative 2, right? We'll do more of that later on, but just to kind of give you an idea, it's always about finding the angle first and then taking that radius and going either forwards or backwards. If it's a negative angle, by the way, you would go down clockwise instead of counterclockwise. This is graphing polar coordinates. This is looking at complex numbers with the modulus, which is the magnitude, which is the distance, and the argument, or the theta, the angle that it is rotated to. Make sure you go back and check those out. Make sure you complete that concept check just to make sure you know what you're doing today, and we will talk to you tomorrow.